Now, I'm not allowed slides for this talk, which makes it quite difficult. Us chemists are terrible at talking to each other without pictures, so we're going to be even worse at talking to other people. So what I've done is I've made some little models of lithium-ion batteries right here. So here's a caramel shortbread. They just get passed around. So this represents a lithium-ion battery. While I was going around, bit of history on lithium-ion batteries. So they were sort of first commercialized in 1991, and since then they've sort of spread their way into every little crevice of our lives. So this is one that I got out of my bike light, but they're also powering all of your mobile phones, they power your watches. Now they're in cars, they're in buses, they are absolutely everywhere, and they're completely essential to how modern society functions. In fact, the Nobel Prize in 2019 for chemistry went to John Goodenough, M. Stanley Whittingham, and Akira Yoshino for the development of lithium-ion batteries. Should mention, M. Stanley Whittingham did his master's and his DPhil here at Oxford, and John Goodenough was working about 5 minutes up the road that way when he discovered lithium cobalt oxide, which is the essential material that won him the Nobel Prize. These little devices, super important, but a lot of people don't really understand how they work. So I'm going to use this to sort of help explain. So here we've got a layer of chocolate, then a layer of caramel, and then a layer of shortbread. And this chocolate at the top represents what we call an anode in the battery. The caramel represents an electrolyte, and the shortbread represents a cathode. And if you imagine the cocoa in this whole system as your lithium ions, basically the lithium up here doesn't like to be there, and it wants to get down into the shortbread. The problem is lithium is associated with an electron when it's in the anode, and both the electron and the lithium want to get down there, but the lithium can't get through this electrolyte layer while it's still attached to an electron. And that's where we come in, right? We plug our batteries into a circuit, and so that's like my fingers, and that gives a path for the electrons to move. And so then the lithium can move down through the electrolyte, and the electrons can move around my fingers. And basically what we do is we've got a device, sort of that's my hand, and as the electrons pass through, that generates a current, and that's what we use to power our device. It's not actually that complicated, it's just stuff wants to go from one place to another, and you just give it two different paths to do it. I don't actually work on batteries, so why am I talking about this? I work on polymers. Let's first start, well, what is a polymer? So we've got some more models. These are less edible. And a polymer is basically a big, long chain of molecules made up of smaller molecules we call monomers. So if each of these links in this paper chain is a monomer, then the whole thing is a polymer. And people often conflate polymers with plastics, and that's not entirely wrong. All plastics are polymers, but not all polymers are plastics. And these things get quite a bad rep. Plastics, people are like, oh, they're terrible for the environment. And that's true. In some cases, they're not great. But to be honest, that's more of a problem with how we use them. Polymers are really amazing materials. They can do pretty much anything we tell them to. We can change like the kind of monomers we use, the kind of links in this paper chain. We can change how long the paper chain is. We can change sort of the dispersity of the paper chain, how long they all are together. We can put branches on it. We can do all sorts of these things. And that can change all the different properties of our polymers to do all sorts of different things. And you probably know some polymers. If I name polythene, polyester, those are pretty classic ones people know about, and they're everywhere, shopping bags and Tupperware containers. But then you've also got things like spandex and Teflon and PVA glue, all are polymeric materials that do all sorts of different things depending on what we've designed them to do. They're also present in nature. So polymers, as I said, aren't just limited to plastics. This is made of paper, right? Paper is mostly composed of cellulose, and cellulose itself is what we call a polysaccharide. It's lots of little sugars linked up together to make, again, a polymer. Same with lignin, which makes up wood. In fact, like proteins are polymers. DNA is really a polymer. These are really, really amazing materials that you can do all sorts of things with. But where do they come in batteries? So firstly, this electrolyte layer I was talking about here, it's often a liquid, but you can make it out of a polymer. And making it out of polymer can be a really good thing. You see all these pictures on the news of buses exploding because their battery has malfunctioned. If you put a polymer layer as your electrolyte, that can actually prevent that. The bit that I'm really interested in is in the shortbread cathode layer that I was talking about earlier. And that's because when you've got this lithium shuttling back and forth through your battery, the lithium, the atoms, they have a volume, and so they're moving back and forth, and naturally they're going to be expanding and contracting this anode and cathode when they move back and forth between them. And because it's not like a bulk material, it's little crystal particles, and as they expand and contract, they sort of mash against each other and they start to macerate each other down. And if you're macerating your different materials in your battery, then that means you're slowly losing capacity, and that means your lithium can't power stuff as well. So to prevent this, what we do is we put a polymer in there, and that polymer acts to buffer how the battery moves, like it does that expansion and contraction, and that stops it from macerating itself down. So at the moment, the one that everyone uses is called polyvinylidene fluoride, and I can go on for hours. It's absolutely rubbish at what it does. It's also about to be banned by the EU because it's what we call a polyfluorinated alcohol substance, and they're terrible for the environment. So we need to come up with some alternatives. One alternative, for instance, as I mentioned earlier, for the anode particularly, is cellulose. Again, it's nice flexible polymer. It buffers the contraction and expansion of the battery. Specifically, it's one called carboxymethyl cellulose, and that works really great for the anodes, but the problem is it's completely incompatible, the processing of it, with the cathode material. So a lot of work is going into developing new polymer binders for this cathode material, and that's what I'm trying to do. So particularly polymer binders, they need to have quite a lot of different properties. So they need to buffer this expansion. That's the key. You need to be able to process them in certain ways. Polyvinylidene fluoride uses a horrible, horrible solvent to do that, and we want to find better ones that aren't going to, essentially kill the workers that use them. And the way we do that is, well, there are lots of different ways we can do that. We can tailor our properties of our polymers in any way we like. The bit that I'm interested in is using two different kinds of polymers. So this is what I call a conjugated polymer, and that means they're a lot stiffer, and they've got these channels on them, essentially. This is actually a pi orbital, for anyone who knows anything about quantum mechanics. And these little channels here, they can let electrons pass through them, and so you can get this electronically conducting polymer. So yeah, plastics can conduct electricity. Fortunately, not the ones that insulate your wires. But if you're conducting electricity, that really helps in your battery from transferring the electrons from your sort of bulk material around the whole circuit. And that's really helpful in things like supercharging, super fast charging. So rather than sort of plugging your Tesla in and leaving it overnight to charge, you can plug it in, do it in an hour if you've got a conjugated polymer there. Problem with conjugated polymers, A, they're rubbish at conducting the lithium ions. So if you coat all of your substances in your conjugated polymer, then you can't get the lithium ions back and forth. To affect this, we use an ionically conducting polymer, which are much more flexible, like this. And together, that's going to help get the lithium out of the cathode and the anode and to the other one, and the electrons at the same time. Problem is, these things, they're incompatible. They don't like each other. If you put them together, they're like oil and water. They do something called phase separation. So how do we solve this? The way I'm solving this is I'm essentially clipping them together like this, if it'll go, like that. And this is called a block copolymer, and this is the kind of things I make. And what's really neat about this method is So it holds them together, but they also do something called microphase separation. They're still like oil and water, but because they can't get too far away from each other, they just separate into much smaller particles. And those smaller particles actually impart really interesting properties onto the polymer itself. So what it means is this flexible bit, when you apply stress to the polymer, it will pull apart and you can flex it. Meanwhile, when you release that stress, these stiff bits, they sort of pin the whole thing in place and will ping the polymer back into place once you release it. And that gives it this rubbery property. This is actually the exact same mechanism that works in styrene butadiene rubber, which is most synthetic rubber. And that's the exact property we need to buffer that contraction and expansion of the anodes and cathodes in the lithium-ion batteries. And that's going to improve our capacity. It means we can get better batteries that last longer, they can hold more charge, they can charge faster. It's really, really useful. But it's not the only thing we're interested in using them for. We are thinking about using them for bioelectronics, for sensors, for making fully flexible batteries. There's all sorts of different routes that this can go, and it's going to be a really fascinating journey over the next few years. Thank you very much. Any questions?